Hi students, today we are going to see the topic on iron carbon equilibrium diagram. Myself Sathish, Assistant Professor Mechanical Engineering Department, working at Akshay College of Engineering and Technology. Before we are seeing the iron carbon system, we have to know the phase diagrams. Phase diagrams are graphical representation of what phases are present in an alloy system at various temperature, pressure and composition. In other terms, a phase diagram is a map showing the structure or phase present as the temperature and overall composition of the materials are varied. Phase diagrams are also known as equilibrium diagrams or constitutional diagrams. Here we are seeing the iron carbon system. This is the basic steel and cast iron formation, how we are getting from the carbon percentage which we are adding in the iron. Iron has been widely used by man for thousands of years. The availability, comparatively low cost, and a wider range of properties have made the iron and steel materials of great importance. Steels and cast irons containing varying percentages of carbon and other alloying elements are very popular engineering material. In fact, iron and steel account for more than 90% of the total tonnage of all metals used today. Because of its outstanding commercial importance, the study of iron carbon alloy in detail is very essential for the engineering. Pure iron is a allotropic metal. Allotropy refers to the possibilities of existence of two or more different crystal structures for a substance depending upon temperature. This phenomenon is also known as polymorphism. The pure iron exists in three allotropic forms: alpha iron, gamma iron and delta iron. This picture depicts the temperature ranges in which allotropic forms of pure iron exist under equilibrium condition. Alpha iron BCC structure stable at temperature up to 908 degrees centigrade. Gamma iron FCC structure stable between 908 to 1388 degrees centigrade. Delta iron body center cubic structure which is having stable between 1388 degree to 1535 degrees centigrade as a melting point. There are different microscopic constitution of iron carbon alloys exist. The study of this microconstitute is essential in order to understand iron carbon equilibrium diagram and are ferrite, austenite, cementite, pearlite, leadberite, martensite, torosite, sorbite and bainite. In this picture, ferrite is the primary solid solution based on alpha iron having BCC structure. It is nothing but the intentional solid solution of carbon in iron. Maximum solubility of carbon in iron is 0.025% of carbon at 723 degrees centigrade, while its solubility at room temperature is only about 0.008%. Ferrite is soft, ductile and highly magnetic. It can undergo extensive cold working. Austenite or gamma iron. Austenite is a primary solid solution based on gamma iron having FCC structure. This is also an interstitial solid solution of carbon in iron. The maximum solubility of carbon in FCC iron is about 2% at 1140 degrees centigrade. Austenite is normally not stable at room temperature, mostly stable only above the critical temperature. Austenite is soft, tough, and highly ductile. Thus, it is more suitable for fabrication process. It is also a non-magnetic or paramagnetic. Austenite has a great electrical resistance and coefficient of expansion than ferrite. Cementite structure. Cementite is named given to the carbide of iron, Fe3C. It is the hard, brittle, intermetallic compound of iron with 6.69% of carbon. The hardness and brittleness of the cast iron is believed to be due to the presence of the cementite. It is magnetic below 250 degrees centigrade. Pearlite. Pearlite is the eutectoid mixture of ferrite 87.5% and cementite 12.5%. It is formed when austenite decomposed during cooling. It contains 0.8% of carbon. It consists of alternative thin layer or lamina of ferrite and cementite. The name derives from its lustrous appearance similar to mother of pearl when viewed in the white light under a microscope. The properties of pearlite is mild way between ferrite and cementite. It is relatively strong, hard, and ductile. Here we can also see the ledubyrite. Ledubyrite is the eutectic mixture of austenite, gamma iron, and cementite Fe3C containing 4.3% of carbon content. In pure iron carbon alloy, it forms an 1140 degrees centigrade. Most of engineering alloy materials belongs to this range of alloy. Pig iron, the most important engineering material, is ledubyrite. Martensite. Martensite is the supersaturated solid solution of carbon in alpha iron. It is formed when a steel is very rapidly cooled from the austenitic state. It exhibits a characteristic acrylate or needle-like structure. It has very hard, more brittle, and low ductile properties. There is an increase in specific volume during formation of martensite from austenite. As a result, internal stresses are set up in the material leading to the formation of mini cracks. Torosite. Torosite is the mixture of radial laminae of ferrite and cementite. In fact, it differs from pearlite only in the degree of fine lines. The constitution is also known as torosite pearlite. It is the microstructure consisting ferrite and finely divided cementite produced on tempering martensite below 450 degrees centigrade. In this picture we can able to see pearlite and ferrite, austenite, primary austenite being solidifying, cementite being solidifying, austenite to pearlite structure, the different ranges of the curves which we can able to see. Sorbite. Sorbite is a microstructure consisting ferrite and finely divided cementite produced on tempering martensite above 450 degrees centigrade. This constitute is also known as sorbitic pearlite. It is formed by decomposition of austenite when cooled at a rate slower than that, which will yield a torositic structure, and faster than that, which will produce a pearlitic structure. Through sorbite, steel is slightly less ductile than pearlite steel. Its tensile and yield strength are high. Thus, sorbitic steels are often known as toughened steel. Bainite. Here we can able to see cementite being sideways below and above the banitic structures in this curve. Bainite is a decomposition product of austenite consisting of an aggregate of ferrite and carbide. Bainite obtains by transformation of pearlite at higher temperature has a feathery structure. It is called upper bainite. Bainite obtained by lower temperature transformation has needle-like or astic structure is called lower bainite. Lower bainite provides high mechanical properties, and that is why it is extensively used for components of machine and structures. This iron carbon equilibrium diagram is very much useful in understanding the microstructure and properties of cast irons and carbon steels. It is also used to understand the basic difference among iron alloys and the control of the properties. In the phase diagram is considered by plotting the carbon composition weight percentage along the x-axis and the temperature along the y-axis. The iron carbon carbide Fe3C phase diagram is shown in the picture now. This phase diagram presents the phase presence at various temperature for very slow cooling iron carbon alloys which up to 6.67% of carbon content in the x-axis. Here in this picture we can able to see the alpha ferrite. This phase is an intestinal solid solution of carbon in BCC iron crystal latite. This picture shows the solid solubility of carbon in the alpha ferrite is maximum of 0.02% at 723 degrees centigrade and decreases to 0.005% at 0 degree centigrade. Here we can see the austenite or gamma iron. The intestinal solid solution of carbon in gamma iron is called austenite. Austenite has a FCC crystal structure and a much higher solid solubility for carbon than alpha ferrite. As indicated in the figure, the solid solubility of carbon in austenite is a maximum of 2.08% at 1148 degrees centigrade and decreases to 0.8% at 723 degrees centigrade. Cementite Fe3C. The intermetallic iron carbon compound Fe3C is called cementite. As shown in this picture, cementite has negligible solubility limits and the composition of 6.67% of carbon and 93.3% of the ferrite mixture we can able to get a cementite. Delta ferrite. The intestinal solid solution of carbon in gamma delta iron is called delta ferrite. Delta ferrite has a BCC crystal structure. In this picture we can see the maximum solid solubility of carbon in delta ferrite is 0.09% at 1465 degrees centigrade. Solidifications of iron carbon alloys. As we know, there are three types of ferrous alloys based on carbon content: iron, steel, cast iron. Compositions up to 0.008% carbon are regarded as commercially pure iron. Those form 0.008 to 2% carbon represent steel and above that 2% carbon represents the cast iron. Steels are further subdivided into eutectoid steel, steels that contain 0.8% of the carbon. The eutectoid amount of the carbon are called eutectoid steel. Hypoeutectoid steel. Steels having less than 0.8% of carbon content are known as hypoeutectoid steel. Hypereutectoid steels, steels having more than 0.8% of carbon are known as hypereutectoid steels. For example, in this picture we can able to see the transformation of hypoeutectoid steel. Now consider a composition to the left of the eutictoid between 0.022 percentage and 0.8 percentage of the carbon. This is termed a hypoeutictoid less than eutictoid steel. In this figure, which illustrates the transformation of a 0.38 percentage of the carbon hypoeutictoid steel with slow cooling. If a sample of a 0.38 percentage of carbon content steel, which we take as a hypoeutictoid steel, is heated to about 875 degrees centigrade, pointing in a figure for a sufficient time, its microstructure will become homogeneously austenite. Then, if the steel is slowly cooled to temperature B, in figure above 775 degrees centigrade, pro-eutictoid ferrite will nucleate and glows mostly at a austenitic grain boundaries. If the alloy is slowly cooled from the temperature B to C, in the amount of pro-eutictoid ferrite formed will continue to increase until about 50% of the austenite is transformed. On further slow cooling up to 723 degrees centigrade, the remaining austenite will transform isothermally into pearlite. By the eutictoid reaction, austenite gives ferrite plus cementite of both the solid structures. In this picture shows a 0.38 percentage of the carbon content steel having a microstructure consisting of pearlite and pro-eutictoid ferrite. In this picture, we can able to see the hypoeutictoid alloys, desulfurized hypoeutictoid alloys. When we fast cooling it, we get the crystal structures when we are seeing it in a microscopic like this. Moderate cooling, the structure like this. Slow cooling, the structure like this we will get. In the fast cooling, we will get white cast iron. In the moderate cooling, we will get pearlitic grey cast iron. In the slow cooling, we get ferritic grey cast iron. Reheating and holding for a 30 plus hours. When we do it a fast cooling, we get a pearlitic malleable structure. Slow cooling, when we did ferritic malleable structure, we get. Desulfurized hypoeutictoid steels, the carbon content of 2.50 to 4% of the carbon. Moderate cooling, we get pearlitic ductile cast iron. In the slow cooling, we get a microstructure as well as the material as a ferritic ductile cast iron. In this iron carbon phase diagram, we can able to see ferrite alpha ion, an interstitial solid solution of carbon in alpha ion having the BCC structure. Here we can able to see the austenite gamma ion, an interstitial solid solution of a carbon in gamma ion having a FCC structure. Here we can able to see the pearlitic structure of alpha plus Fe3C, the microstructures, the eutictoid of ferrite and cementite with a laminar microstructure of alternate alpha ion and cementite pearlite plates. Like this, each microstructures having the pearlite, leadberite, martensite, taurisite, sorbite, pearlite like the structures we can get in this iron carbon phase diagram. Now we can see the applications of the steel in construction, low and high rise building, educational, hospital buildings, sports stadiums, stations, reinforced concrete bridge, deck plates, piers, suspension cables, harbors, canals, flooring, office, tunnels, security, fencing, coastal and flood defenses. Also in transport of the thing which we can see the steel applications like trucks, transmissions, trails, rail, ships, anchors, jet engine components, aircraft undercarriage. In energy side, oil and gas wells, platform pipes, electricity lines, wind turbines, etc. Packaging section, we can able to see steel packaging products goes from water, air, and light exposure, and it's fully recyclable. Appliances and industrials, we can able to see about 75% of the weight of the typical household applications comes from steel. Steel is found in appliances like fridge, washing machine, ovens, micro ovens, sinks, etc. That's all for today's section, students. Thanks for listening.